Good afternoon. I basically, today I wanted to give you an overview of the predictive model that I built to estimate the net hourly electrical energy output of a power plant. The data essentially included a 9,568 hourly observations from plant sensors, environmental variables such as ambient temperature, exhaust vacuum, ambient pressure, and relative humidity um, were included. The target variable was net hourly electrical energy output, abbreviated as PE. It's measured in megawatts. So um, my modeling approach, essentially the first step was to identify the correct, obviously the correct modeling approach. And since the net hourly electrical energy output is a continuous numerical value, this is a supervised regression problem. The goal is not to classify the output into categories, but really to predict an actual energy output value. I used the four available environmental features as inputs because each one of them influence the power plant efficiency and generation performance. As far as the model building, um, I basically I prepared the data for model building. I split the data set into a training set and a test set, and using 80% of the data for training, 20% of the data for final testing. Additionally, the test set, I kept it separate until the end so that I could evaluate the final model on data it had not seen before. Next, as far as model building is concerned, I did model comparison. And ultimately, to compare the different models, I used the five-fold cross-validation on the training data. This helped create a more reliable comparison because each of the models was trained and validated across multiple splits of the training set. So essentially multiple data splits of that training set. That's how it was validated. And then comparing several regression models, including linear regression, ridge regression, random forest, gradient boosting, and histogram gradient boosting. Next, the best performing model during the validation was the histogram gradient boosting. This model performed better than the linear models because it can capture more complex non-linear relationships, the environmental variables, and power plant's energy output, while linear regression was used as a simple baseline. The gradient boosting model gave stronger prediction performance, the stronger prediction performance than anticipated. And then model evaluation portion. For the evaluation, I used the root mean squared error as the main metric because it measures prediction error in the same units as the target variable, megawatts, and it penalizes the larger errors more heavily. So that's why I decided to use the root mean squared error. I also looked at the mean absolute error and R squared to better understand the model's performance. On the final test set, the histogram gradient boosting model achieved a root mean squared error of about 3.32 megawatts, a mean absolute error of 2.47 megawatts, and an R squared value of, excuse me, 0.962. This essentially means that the model explained about 96.2% of the variation in electrical energy output on unseen data. The mean absolute error, excuse me, also tells us that the average, the model's predictions were about 2.47 megawatts away from the actual value, which includes indicates strong predictive strong predictive accuracy. Finally, the model interpretation. Most important feature was the ambient temperature, followed by the exhaust vacuum, relative humidity, and finally ambient pressure. This makes sense because the pressure has a major impact on air density and power plant efficiency. Exhaust vacuum also has it plays an important role because it relates to turbine and condenser performance. Overall, the final model performed well and met the project goals. It used the correct regression approach compared to multiple models through cross-validation. Through cross-validation and evaluated the final model with appropriate regression metrics. So that's essentially the model interpretation. And then I'll show you a screenshot of the final output of the model that I created. Here's a screenshot of the final model output. You'll see, of course, the linear and ridge regression had the highest megawatt prediction at 4.57. And then the actual versus predicted had a very low error rate as far as the variation of the megawatts that were predicted. So all in all, I was actually extremely pleased with the model performance. And ultimately, it was an insightful experience kind of working through the model prediction and some of the machine learning algorithms that we learned in this section. All right, thank you.